Okay, let's start. So today we will talk about backpropagation and networks. First, we will talk about backpropagation. Previously, we have a so-called score function. We have the weights serve as the parameters in the score function. And then we have some loss functions to evaluate this weight, how good the weight works for the score function. This loss function is supposed to evaluate how well the weight works for the score function. And the overall loss function can be written as the sum of all the loss function results and some regulation item. Here we use the L2 regulation to make each weight parameter similar to each other. In this lecture, we will learn how to adjust the weight to achieve lower loss function results. We can do that by grading the descent. This is the equation to help you to compute the gradient. We can do the numeric gradient, but it's very slow and approximate. Although it's easy to implement. But in fact, we use the analytic gradient, which is the fastest. But we also may have some mistake by using this analytic gradient. We will introduce those errors in the following slides. Here is the computational graph for a neural network. We have the weight, we have the input, and we do a inner product here to get the result here. And then we send the results to the loss function and some regulation term. And then we have the final loss function. We can also write a real neural network, for example, the convolutional neural network, particularly the AlexNet in this form. We have the input, which is image, and we have the weights, includes multiple layers here. Each layer has its own weight matrix, and then we have the loss here. We can also plug another neural network like like a transformer into this pattern, into this computational graph. And then we can use the so-called backpropagation to compute the gradient descent. So here is one simple example. We have a function like this. In this function, we have three variables, x, y, and z. And we can assign some value to these three variables. Here are values. And this is the computational graph for the function f. We do addition here, and then do the multiplication here, and then get the results. When we plug the values of the inputs to here, we have the intermediate results like this three, and like this three here, and then we have the final output. So you can compute it yourself. when we do the back propagation, we need to break this function of this equation into different pieces. So how can we do that? We can make an intermediate variable like this q, and let the q equals to x plus 1. And then we can rewrite the f function as q multiply z. By decomposing this function, we can do the analysis. For this simple equation, we can do the so-called partial derivative. For example, here we do the partial derivative with respect to x, or do the partial derivative on y. If we do that on x, the result is 1. If we do the partial derivative on y, the result is still 1. So if you do not understand these equations, you can Google the basic. For this equation, we can do the partial derivative on the result is z. If we do the partial derivative on z, the result is 2. So what we want to have is these three terms. We can compute them in a recursive way. First, we can compute this item. So if we do a partial derivative on x, the result here is 1. Why? Because the function is f itself. Next, we will compute this term. How can we do that? We just do a partial derivative on the z. By this equation, you know the answer here is a q. The q in this graph is 3. So the result here is 3. And then we can do this, compute this item. So if we do a partial derivative on q, the result is a z. The value of z is a minus -4. So here we have a -4. Next, we will do a partial derivative on y. We can apply the so-called the 10 rule. We first compute this one, which is the we first compute this one, which is the value of this. And then we can compute this. So for this item, we can actually use the equation here. The result here is 1. So when we use -4 multiplied 1, the result here is a -4. For this one, we can apply the chain rule. This is -4. Why? Because this is always -4. And then we can apply the equation here. The result is 1, so we still use the -4 multiplied 1. And then we can have this -4. Any question? So from this computational graph, we can always compute the apply the chain rule, compute the output first, and then get into the backward computation step by step. First, we compute the output here, and then we compute this one, and then we compute this Q. After we have the Q, after we have this, we can continue to compute the Y and X. So here is a simple example. So basically, from a local perspective, you don't need to care about the output. The only matters is the result here, because by this result you can compute the derivative for this for X and Y. So after I give you this value, you can compute these two. To have this. And then this. The so-called chain rule means after you have this, you only need to compute another one at the next back propagation step. So this is so-called a local gradient. And then you can continue to compute the next step after you complete. So this is so-called a recursive way. Why? Because what we got for this function on neuron, you can continue to do that. The same thing for this one. Here is another example. This example is a softmax function. However, instead of x here, we have x0 and x1. We also have 3 parameters, w0, w1, and w2. So in order to do the backpropagation of this function, we need these equations. And in these equations, we only have one term. All right, this is the x. When we do a partial derivative on the x, or do compute the gradient on the x, we have this. If the function is e2x, this is the partial derivative. And if we have an ax, the result is a. If we have an x2 minus 1, and this is the result. If we have a c plus x, the result is 1 here. Then we can compute the back propagation one by one. Again, for the forward part, you can easily plug the value of these inputs into the equation and then compute the intermediate results here and then the final output here. But for the beginning of the back propagation, you need to compute this. The output here, if we call the function f, if we do a partial derivative of f with respect to f, the result is 1. So this is the beginning of the back propagation. Since the local function for this one is x2 minus 1, we need this equation. And we know the result is this one. So we just need to plug the x value into the equation here. What's the value of x? The value of x is 1.37. So the partial derivative item is here. Because of the chain rule, we need to multiply this 1 here. So this is the result for this step. And then we need to do the back propagation for this local function. For this local function is the x plus 1 or x plus c. C is 1. When we do the partial derivative with the respect to x, the result is 1 here. Which is irrelevant to the value of x. So we can write a 1 here, but multiply this one. Because of the chain rule. This is the partial derivative value. Because of the chain rule, we need to multiply this one. The next we will compute the ext, e to x function. We do the partial derivative. The result is still e to x. And the x value here is minus 1. So this is the partial derivative item. And this is the chain rule. And then we have that result. The next local item is the addition here. We first need to compute the derivative. The partial derivative is 1. Why? Because of this one. Plus here, when we do the partial derivative, the result is 1. So we have the 1 here, and we just need to multiply. Because of the chain rule, we need to multiply this one. So both of them, so for both of them, the result is 1, 2. Again, before this, we have another class. We have another addition. For this addition, the partial derivative is 1, and because of the chain rule, we multiply 1, 2 here. So the result for these two is actually 1, 2. And then we have this. This is a multiplication. For the multiplication, we have this. here we have W0 multiplied W0 multiplied X0. So if we do a partial derivative on W0, the result is X0. If we do the partial derivative on X0, the result is a W0. This is why it's W. Value of W0. This is why if we do the partial derivative on X0, we have this. This is we do the partial derivative on the W on X0. Because of the chain rule, we have to multiply 0.2. And then we have these results. So for this part, we have the same thing. We can compute it yourself. So we can consider the W0 X0 plus W1 X1 plus W2 as a large X. So if we do that, this is exactly the sigma function. And then if we do a partial derivative of this function, X, we have this. And then we can rewrite the partial derivative in this form. By subtraction and the multiplication, we can compute the partial derivative. This is exactly the breakdown of this sigmoid function. Because the X here is 0.73, if we plug this value into this function, we can directly have the partial derivative here as 0.2. So there are some patterns in the backward computational flow. For example, the addition. Here is the addition. If we do backward back propagation plan on a add gate, what can be achieved? We just distribute the value here to both directions. Both of them will have the same value testing. Why we have this denominator? Because the partial derivative of addition is 1. So we use 1 multiplied by this one. So what's the function of X? What's the function if we have a max function? The max function will compare the value of Z and W in this case. The Z is a 2, W is a -1. Of course, Z is larger. So the result here is this. So if we do a partial derivative on the max function, on a comparison function, it can achieve some function like the gradient alpha, which means that only one part, more specifically, the larger one will have this gradient. In this case, Z is larger, so Z has this, but the other one has a 0. So the function of the multiplication here. It's a kind of a feature. What does the feature mean? Feature means you have the value for x as the source, and you also have the value of y as a -4. When you have a 2 here, and this is a multiplication gate, after you compute the gradient for these two, you actually find out for this one, you actually use the value of y, multiply this one. For this one, you actually use the value of x, multiply this one. So somehow, the gradient here are the switching of the value of x and then y. Of course, it's the switching of the x and y multiply this two. When we do the back propagation, here is two examples, are just simple example. We only have one single number, but in fact, we always handle the matrix in the neural network applications. So somehow the gradient here is a vector, and these value of these two are also vectors. For this max function, the input vector is 4k, and output function is also 4k. If we compute the gradient on this function, the gradient will be 4k multiplied 4k matrix. So somehow the gradient can be very large. Here is one example of the backpropagation of a vectorized example. The input x here is n element vector, and the weight w here is a matrix of n times n. The function of f is the square function. Which can also be written like this. We use the w multiply x and then do a square function and sum the result together. So we can rewrite function into this combination of graphs into a matrix multiplication or vector matrix multiplication here, and then do a L2 independence. Input in this example for W is and X is a 2-element vector. How to achieve this result? We just use this value, multiply this value, multiply this one, and sum them together. The result is this number. We can also use this number, multiply this one, plus this number, use this one. The result is this number. So here is just a matrix vector multiplication. And the result of that multiplication is also a 2-element vector. And then we do a L2 distance. L2 distance means do a square on this element, do another square on this element, and sum them together. The result is a single number. This is the forward part. For the backward part, first we do a partial derivative of f is respective to f itself. So the result here is 1. And then we will do partial derivative on this L2 function. L2 function is x to 2. After we do the partial derivative, we have the 2x or 2q. We rewrite the x as a qi. So this is the input. We just multiply this actually by 2. Each element by 2, actually. And then we need to continue to do computer gradient for this multiplication function. Remember, we have a so-called this multiplication gate as the switch gate, which means that if we want to compute the gradient for this one, we need to use this one multiply this one. If we compute the gradient for this one, we need to use this one. So in this example, we first compute the gradient for this one. So we need to use this to multiply this. How to do that? This one multiplying this one is the first element. This one multiplying this one is the second element. And then when multiply, use this, multiply this. Multiply this, sorry. This one multiply this, we have, I'm sorry. If I use this one to multiply this one, I can have this result. So we have a 4 element wise multiplication, actually. The gradient should have the same shape as the input. If the input is a 2 times 2 matrix, the gradient here is also a 2 times 2 element matrix. So if I want to compute the gradient for x, then we just need to use this matrix multiply this one. And this equation can help you to compute that. First, we need to do a transformation on this matrix. And then we can use 1 point, and then we can use 0.1 multiply. So you can compute the first element of X in this way. Before you actually do the computation, you need to do a transportation on the W. In the same way, you can compute the second element in the X vector. Again, the gradient of X should have the same shape or dimension as the unit. So this is so-called a vectorized example. Overall, we can perform the back propagation in a recursive way. And then we can also apply the chain rule. So in the forward part, we compute a lot of intermediate values and we store them in the memory. During the backward pass, we can reuse those intermediate results to compute our gradients. Now we have a score function, W multiply X. So if we want to build a two-layer, after we apply a log function or nonlinear operation on the result of the score function result of the first layer, we can attach another layer to here. So this is the graph for the two-layer neural network. We have the input, and then we have the weight. We do a multiplication and the result of the first layer, and then we can apply a so-called max function, a nonlinear function on the result here, and then multiply the weight of the second layer, and then get the final output. So by different linear layers, we can actually stack them together, but we need to insert a so-called nonlinear function. This max function is actually a ReLU function. And then we have the final score function. This final score function can indicate the possibility for 10 class because we have 10 elements in this case. So if we want to build a 3-layer neural network, we continue to apply a nonlinear operation on the output of the second one, and then multiply another weight matrix. Because of the neural function, the curious researcher actually studies some working mechanism of the biological synapse, and then they build a mathematical model for that. In the mathematical model, we have ways, we have bias, we talk about this, and then we can do the inner product operation between the weights and the inputs. Besides this, people also learn so-called activation function is very important in this mathematical model. The so-called activation function is a nonlinear function. The so-called nonlinear function means we need some nonlinearity in this function. Sigmoid is one of the nonlinear function we can use. And we talk about the sigmoid, how to do the backpropagation for this sigmoid in previous lines. Besides the sigmoid, we also have some other activation function. And this is the max, zero and max function, which we also call it the ReLU function. And we use this ReLU function a lot. We have a score function and an activation function, and then the loss function. We basically have all the essential components for a neural network. By these components, we can build a multiple layer neural network. Of course, the first layer is always the input layer. And then we have a W, which is a linear layer. After this linear layer, we can have an activation function. And then we can generate the output. So this is so-called one single layer. And we also call a hidden layer. And the hidden layer consists of one linear layer and one activation function. We can also have a three-layer neural network or two hidden layer neural network. So for this example, here is one hidden layer and another hidden layer. Inside each hidden layer, we have a linear layer, which is the W matrix and a activation function. Of course, by stacking more layers, we can achieve higher accuracy. So any question? So in this lecture, we introduced three examples to compute backpropagation. We have two simple example and one vectorized example. You don't have to, you don't have to recite the partial directive function, because the computer can easily do these for you. Besides the partial directive function, we also have the chain rule. And you also need to remember the final dimension of the gradient should be the same as the input. So that's all for the backpropagation. If you have no question, we can stop today. Thank you very much.